Okay, so let's continue our discussion of polysilicon thin film. Polysilicon thin film is the most popular structural material in certain micromachining. And it can be used as the structural layer, conductor, piezo resistor, and temperature sensor. And so polysilicon has many important applications in surface micromachining and also in the broader MEMS field. Polysilicon thin film is typically prepared using LPCVD method, low pressure chemical vapor deposition. The gas used is silane. As deposited polysilicon thin film typically has a compressive strain, a compressive stress. There with high temperature annealing, 1050 Celsius, high temperature annealing. The compressive stress can be quickly reduced to almost zero within half an hour. Well, we also briefly discussed mechanical stress and the strain. The strain is defined as a delta L over L naught by epsilon. Stress sigma defined as F over A by the force per unit area. If this beam is stretched, then strain and stress are positive. If the beam is compressed, then the strain and the stress are negative. The positive stress is also called tensile stress. Negative stress called compressive stress. And it is shown in the following figure. The tensile stress can cause concave bending of the substrate, and compressed stress leads to convex bending. Just a moment. Okay, now let's take a look at ion implantation. Note that this is the dominant method to introduce impurities, or the method to dope silicon or polysilicon. This figure shows a schematic of an ion implanter. The bottom part is an ion source, or the source that generates ions, right, such as boron ion, arsenic ion, and phosphorus ion. The ions are simply generated using plasma. So it's simply a plasma. We have two electrodes, okay, to generate plasma. Then the ions generated in the plasma are extracted and accelerated toward the stage, the next stage, which is called mass separation stage. Okay, this stage is used to separate different ions. Right? For example, if we only want to choose boron, right? And this stage will select the boron and block other ions. The operating principle is shown of the mass separation stage is shown in this figure. Right, this separation stage takes advantage of a perpendicular magnetic field. So as shown in this figure, this magnetic field is perpendicular to the screen and points out of the screen. Okay, it's pointing toward you, okay, not into the screen. It points out of the screen. Then the incident, okay, the incident ions has a velocity in this direction. Then this ion will experience a Lorentz force, right? The movement of a charged particle in magnetic field. So this ion must experience a Lorentz force. What's the direction of this Lorentz force? I hope you still remember how to calculate the Lorentz force. F is equal to Q V cross B. Right? Now V is in this direction. B, right, is perpendicular to the screen and points out of the screen. So V cross B is in which direction? Well, with the right hand rule, right? And the Q is positive. So the Lorentz force is in this direction, right? That's the direction of this Lorentz force. Therefore, the incident ion enter this mass separation stage will be deflected downward, okay, deflected downward, and follow this circular trajectory, okay. Any question? And this Lorentz force will serve as a centripetal force, right? QVB should be equal to mv squared over r, where v is the magnitude of the ion velocity, right? The incident velocity. Q is a charge, m is an ion mass, right? B is a magnetic field, and r is a radius of curvature, right? This distance, radius of curvature. If the ion obeys the classic mechanism, or if the energy of the ion is simply equal to the kinetic energy, namely E is equal to half mv squared. Right, this is based on the classical mechanics, right? The kinetic energy. Then we can calculate the velocity of ion. So V is simply equal to square root 2E over m. Right? E is the energy of ion, and the energy is equal to Q V exit. Okay, so this V exit is the voltage, the potential of this electrode. Okay, so the energy of the ion is equal to QV. So this is the velocity of the incident ions. Then the bending radius, okay, from equation, from this top equation, we can calculate bending radius R, right? Since now V is given. So R is equal to NV over QB, which is 1 over B times the square root 2M over Q times the exit voltage. So we can see that the bending radius, or this radius of curvature, okay, radius curvature of this trajectory is a function of the ion mass, right? Almost accurately, mass over charge ratio. Different ions have different mass or different mass over charge ratio. Thus, different ions, okay, when they pass this mass separation stage, they will have different bending radius or radius curvature. So only the desired ion can pass this thin slit on the exit of the mass separation stage. Right? So ions with the right mass over charge ratio will have the right bending radius. Then they can pass this thin slit. Other ions will be blocked by this plate. Then the selected ions are accelerated to very high speed or very high energy and implanted into the substrate. So this is the operating principle of an ion implanter. Questions? Distribution of implanted ions. To a first order of approximation, Gaussian distribution can be used to model the distribution of implanted ions, right? Namely, n should be equal to phi over 2 square root 2 pi delta Rp times e to the power of negative x minus Rp square over 2 delta Rp square. Note that Rp is the average implantation depth. Delta Rp represents the standard deviation or scattering of the ions in the longitudinal direction. These two definitions are also illustrated in this figure. Right? Rp is the average implantation depth. Delta Rp represents the standard deviation, right, along this direction, along this depth direction. This figure plots the distribution of implanted boron ions with a different implantation energy. The dashed lines, okay, these dashed lines represent the theoretical Gaussian distribution, and the solid lines represent the real distribution. Then we can observe that the tails of real distribution deviate from the theoretical Gaussian distribution. An explanation is that boron ions experience significant backscattering when they collide with a silicon atom. That's why we observe this kind of tails. This figure plots Rp, okay, which is the average implantation depth, right, or this distance. Okay. Right, this distance is the RP, right? Average implantation depth, right? That's RP for 800 kilo EV energy. So this figure plots RP as a function of implantation energy. Okay, RP for boron, phosphorus, and arsenic in silicon and silicon dioxide at various energies. The solid lines represent the result for in silicon. Dashed lines represent RP in silicon dioxide. Let's take a look at the boron curve, right, the top curve for boron. Let's assume that we have a 0.4 micron polysilicon. And the polysilicon is a 0.4 micron thick. And we want to dope this polysilicon thin film using boron. And the average implantation depth, RP, should be half of the thickness. Namely, we want RP to be 0.2 micrometer. We want the average implantation depth to be right in the middle of the thin film. So in order to achieve this 0.2 micron RP, how large is the implantation energy? How large the implantation energy we should choose? Then we can use this curve, right? This is the 0.1, right? This is 0.1 micron. So 0.2 is this line. Right? This line stands for 0.2 micron. Okay, then we can find this data point. Then we go downward, okay? We go downward. So how much in energy? 10, 20, 30, 40, 50, 60. So the energy we should choose is a 60 keV, right? Note that the energy is right at the unit of kilo EV. Okay. So this is how we use right, this figure to determine the implantation energy. Next, let's discuss diffusion. In microfabrication community, right, diffusion has two meanings. First, it refers to the movement of atoms or molecules due to concentration gradient. Right, this is actually the commonly known meaning of diffusion. In addition, right, in microfabrication, it also refers to another method to introduce impurity to silicon or polysilicon by taking advantage of the diffusion, right? By taking advantage of the movement of atoms or molecules due to concentration gradient. That's the second meaning. Previously, we just introduced ion implantation. We can use ion implantation to dope single crystal silicon or polycrystal silicon. And then we can also use a diffusion to dope or to introduce impurity to silicon. For example, we can deposit a thin film containing the dopants for example, containing boron or phosphorus. Then we perform a high temperature annealing. And at a high temperature, dopants in this thin film diffuse into the substrate due to the concentration gradient. Right? So we can take advantage of diffusion to introduce impurity to silicon or to dope silicon. The basic equation that describes diffusion is a fixed first law. Namely, J is equal to negative D partial C over partial X. Note that C is an impurity concentration, which is a function of both position X and the time T. So this J is a net flux of material, right? The net flux of material, right? The number of, okay. Just a moment. So J is the net flux of material, namely the number of molecules or atoms passing unit area at unit time. So what's the unit of J? It should be number of atoms or ions per meter square times a second, right? So number of molecules or ions passing unit area at the unit time. That's the fixed first law. Oh, by the way, D is a coefficient of diffusion. Okay. This D is a coefficient of diffusion. Typically, we assume D is a constant. So we can say this flux or the diffusion current is proportional to the concentration gradient. Right? This partial C over partial X is simply the concentration gradient. Okay, and this negative sign means that the atoms or molecules always diffuse from high concentration to a low concentration. Next, let's consider a differential volume element in a bar of cross-sectional area A. Okay, this is a bar structure. Okay, and we consider this a small differential element whose length or thickness is a dx. Okay, very small thickness. And J2, okay, this flux, right? This flux is the material flux due to diffusion. This J2 is a flux leaving the volume, right? Leaving this differential volume, okay, based on the direction, right? It flows out of this volume. And the J1 is a flux entering the volume. Okay, so one is leaving, one is entering. Then if these two fluxes are not the same, they are not equal, the concentration of the diffusing species in the volume must change, or the number of diffusing species must change in this different volume. Right? This is a kind of common sense, right? And the number of impurities in this volume element is simply equal to the product of the concentration and the differential volume element. Right? So the number n, okay, should be equal to the concentration times the volume, right? The volume is A times dx. Right? So this is volume. Concentration times the volume gives you the total number of impurities inside this differential volume. Right, then we come up with this following continuity equation, or this is also mass conservation equation. Right, the left side is the increased rate of diffusers in the differential volume. Right, then the left side is actually dn dt, okay, or we can do partial, okay, so say the function of partial this over partial t, right? Everything can be partial. Let me change d to partial sign. Partial derivative of n with respect to t. Okay, and a times dx, that's a constant, so we can move this out of this this pair of parentheses. So left side becomes a dx times the partial derivative of c with respect to time t. Okay, so that's the left side. That's the increased rate of diffusers in the differential volume. The right side is a negative a J2 minus J1. Right? If J2 is equal to J1, the increase rate is 0. So C the constant. Right? But if J2 is not equal to J1, these two fluxes are not equal, then C must change with temperature. Right? So partial C over partial T is not 0. Then we can divide both sides with a dx. Okay, so left side become partial c over partial t. Right side a will be cancelled. So it's simply partial j over partial x. And j is a net flux of a material. So we already know j in first law. So we can replace j with d times the partial c over partial x. So finally, the right side becomes d times the second partial derivative of c with respect to x. Okay, the left side is a partial c with respect to time. The right side is a second derivative, partial derivative of c with respect to x, the position. So this is a partial differential equation. Solution of fixed law, namely solution of this partial differential equation. In order to solve that partial differential equation, well, we need a boundary and the initial conditions. So let's take a look at case 1. Case 1, the concentration at the surface is fixed. This is actually represent the diffusion example, right? Namely this example. For this example, we can assume the concentration is a constant at the surface. Right, so we have this boundary condition. C, right? C the concentration with the function of both position and time, right? So now the position at the position 0, C 0T is always equal to CS, right? We know that CS is a surface concentration. okay, which is fixed. In addition, we assume C, Z. Well, now we use a Z to represent the position. It's the same as X in the previous slide. At the time 0, now T is equal to 0. Okay. At the time 0, the concentration everywhere is 0. Okay. So there's no impurity in silicon at the time 0 initially. Okay, so that's the initial condition. Then the solution of the Fick's law is given by this formula. C, which is a function of both Z and T, is equal to CS. Right, CS is the surface concentration times ERFC. ERFC actually simply stands for complementary error function. Complementary error function. So the solution is a complementary error function. And this figure plots the normalized concentration as for different diffusion time or different square root of dt. Okay, square root dt of 0.15 micron, 0.2 micron, and 0.25 micron. Next, let's take a look at case 2. The total number of dopants is constant. This actually represent what? Represent the ion implantation. Right? For ion implantation, the total number of dopants is a constant. Then we have this boundary condition, right? The integration of the concentration from 0 to infinity should be equal to a constant, like Qt. Right, this is actually the total, or more accurately speaking, this Qt is the total number of dopant per unit area. Okay, right. C is the unit of C is C is 1 over meter square, right? Sorry, meter cubic. So integration along dz, we end up with a Qt. So it is 1 over m squared. So that would be the total number of dopants over a unit area. So that's the boundary condition. Another boundary condition is that dc dz should be equal to 0 at the position 0, namely at the surface. At the surface, dc dz should be equal to 0. What is the physical meaning of dc dz, or the derivative of c with respect to position? That's simply concentration gradient, right? So this boundary condition tells us that the concentration gradient is 0 at the surface. Then from Fick's first law, right? J is equal to D times concentration gradient. So with a 0 concentration gradient, J is 0, namely the flux is 0. So this boundary condition tells us that no impurities leave or enter the surface. Across the surface, the flux J is 0. So that's another boundary condition. And again, we assume initially there's no impurity in the silicon substrate, right? At time 0, C is equal to 0. So with these kind of boundary and initial conditions, the solution is a Gaussian distribution. C equal to qt over square root pi dt times e to the power of negative z square, right? Z is the distance, okay, divided by 4 dt. The bottom figure plots the concentration, again, the normalized concentration, right, for different diffusion time or different square root dt. Now we can see that for this case, for second case, the slope, okay, the slope is 0 at the surface. So there's no impurities enter or leave the surface. But note that a diffusion coefficient D is a function of temperature. It's actually equal to D equal to D0 times the exponential function of negative EA divided by KT. This relation is typically called Arrhenius relation. It's a fairly famous relation. EA is called activation energy. This is EA, right? Typically between 1 eV and 3 EV. KT, what's the KT? Like KT is called thermal energy, right? The thermal energy of the ions or atoms or molecules. This figure plots diffusion coefficients of various materials in intrinsic silicon, or in silicon. Note that the horizontal axis is 1000 over T, right? So the temperature is higher on the left side, okay? So if we go from right to left, the temperature is higher, right? So it's 1000 over T. And in this figure, we can observe arsenic, boron, and phosphorus. They are the main doping materials for silicon. Some is a p-type, some is a n-type. We can observe that they have very small diffusion coefficient, okay, at the lower part of this figure. Right? So they have very small diffusion coefficients. This is actually desirable because this means phosphorus, boron, and arsenic are very stable in silicon at room temperature. Okay? If the temperature is not very high, they are almost fixed inside the silicon substrate. And this means that the device performance will be very stable. So this is desirable. We actually want the dopants to have small diffusion coefficients. On the other hand, we can see that some materials have fairly large diffusion coefficients, especially metals. For example, lithium, gold, sodium, potassium, they have large diffusion coefficient. So they can move quickly inside the silicon. This is not desirable. So they are not CMOS compatible. Right? Namely, they may contaminate CMOS circuits. Right? CMOS circuit will be contaminated by these metals. If they enter the silicon substrate, the doping condition can be changed quickly, but then the device performance will not be stable. So they are not CMOS compatible. Right? During CMOS fabrication, we should avoid these materials, right? These metals. Now let's take a look at a specific example of doping polysilicon using diffusion. In this example, we use a PSG. I know that PSG stands for phosphosilicate glass. It is a source of phosphorus, but later we will have a more detailed introduction. But we use the PSG as a doping source for polysilicon. As shown in this figure, we first deposit and pattern of sacrificial PSG layer. Okay, this is the first PSG layer. Then deposit and pattern the polysilicon layer. Right? This polysilicon layer serves as a structural layer. Then deposit the top PSG layer. Right? So there are two PSG layers in this process. And know that the PSG is used as both a sacrificial material and the doping source. It serves two roles. Then we anneal this wafer at 1050 Celsius for 1 hour. Then phosphorus in PSG will diffuse into polysilicon from both top surface and the bottom surface. Right, this is the doping is caused by diffusion. And this results in a 1.5 milliohm centimeter resistivity on a 2 micron thick film with a near zero building stress. Right, so there's a high temperature annealing also reduce the building stress of the polysilicon. Summary of polysilicon. The deposition temperature is just below the atmosphere to crystalline transition, namely slightly below 590 degrees C, followed by annealing at 1050 degrees C for 1 hour. So this high temperature annealing can reduce the building stress to almost zero. Deposition pressure about 200 millitorr. Deposition chemistry, silane diluted in hydrogen carrier. The building stress after high temperature annealing is at about -20 megapascal. And we can achieve pretty good film uniformity, quality, and step coverage. It is worth noting that the grains of polysilicon are randomly oriented, by random crystallite or grain orientation. This leads to isotropic mechanical properties. So polysilicon has an isotropic mechanical property. Okay, this is different from single crystal. For single crystal silicon, its mechanical property is anisotropic. Namely, its mechanical properties depend on crystal orientation. Right, so single crystal silicon is different from polysilicon in terms of mechanical properties. And one is anisotropic, the other is isotropic. Silicon nitride, well, this is another widely used thin film in surface micromachining. In MEMS, silicon nitride can be used as a structural layer due to its high mechanical strength. It can also serve as a thermal insulator, electrical insulator, diffusion, and oxidation barrier. So actually, most of the materials have very low diffusion coefficient in silicon nitride. So silicon nitride can serve as a diffusion or oxidation barrier, and also masking layer for anisotropic etching, like for example, KOH or TMH etching. But processing of silicon nitride. Silicon nitride is typically deposited using this chemical reaction. Dichlorosilane reacts with ammonia, forming silicon nitride thin film. Right, so that's a chemical reaction. Note that this we typically use a low pressure chemical vapor deposition to prepare silicon nitride film. This method gives us the best quality of silicon nitride thin film. Deposition temperature between 700 and 900 Celsius. Deposition pressure 300 to 500 millitorr. So it's a low pressure process, right? Low pressure process. Gas flow ratio of dichlorosilane and ammonia is typically 1:3 to 1:4, right? Between 1:3 and 1:4. But in the chemical reaction, the ratio is actually 3:4, right? It's 3:4. And we use 1:3 or 1:4. Right, so with this ratio, there is more nitrogen than required. Right, there's more nitrogen than required. Then what we get is a stoichiometric silicon nitride, namely the silicon to nitrogen ratio is 3:4, right? Same as this, okay? Same as this ratio. Right? This is called stoichiometric silicon nitride. So with this overflow of ammonia, we get stoichiometric silicon nitride. And this silicon nitride has a very large tensile stress, right? 2 to 2 gigapascal. So stoichiometric silicon nitride can easily crack, right, due to its large tensile stress. Etching of silicon nitride. If we use a wet method, then we need to use this phosphoric acid, and the etching temperature is 120 to 200 Celsius. So very high temperature for liquid etching. Right. So this is actually a pretty dangerous process. Dry etching. We can also use a dry method to etch silicon nitride. Right. Simply fluorine-based plasma etching, for example, CF4 SF6. Right, we can use a fluorine-based plasma to etch silicon nitride. Low stress silicon-rich silicon nitride. Please note that the stoichiometric silicon nitride has a very large tensile stress, so it can easily crack. So what we use in MEMS is a typically low stress silicon-rich silicon nitride, not stoichiometric silicon nitride. Let's take a look at this figure. Right? This figure plots residual stress as a function of dichlorosilane over ammonia ratio. But if we use a ratio of 1:3 or 1:4, okay, so the ratio is 0.3 to 0.25, okay, so less than 1, a small ratio, gas flow ratio, then this gives us a very large stress, okay, very large stress. Right. Then we can observe that if we increase this gas flow ratio, namely if we increase the amount of dichlorosilane, then the residual stress will decrease. Okay, so the higher the ratio, like this gas ratio, the smaller the residual stress. We typically use a gas ratio of 4. Okay, we choose a dichlorosilane over ammonia ratio of 4, and 850 Celsius temperature. Right, this gives us a low residual stress. So now we have this ratio of 4, right? Compared to the ratio in this chemical reaction, right? The ratio is 3:4. Right? So with this ratio, with the ratio of 4, there is more silicon required, right? So we actually kind of overflow dichlorosilane. We provide more silicon than required by the stoichiometric ratio. And this gives us silicon-rich silicon nitride. You see, now the silicon to nitrogen ratio is 1 to 1.1 compared to 3:4, right? Compared to 3:4 ratio. The silicon nitride has more silicon. So that's the reason we call this silicon-rich silicon nitride. Okay, it has more silicon than the stoichiometric ratio. And this silicon nitride has a much lower stress. So we call this thin film low stress silicon-rich silicon nitride. Okay, that's the silicon nitride we typically use in MEMS. Right? We do not use a stoichiometric silicon nitride. And we use this low stress silicon-rich silicon nitride. Its Young's modulus is between 260 and 330 gigapascal. Fracture strain 3%, right, very large. Dielectric constant somewhere between 6 to 7. Silicon dioxide. Know that silicon dioxide can be prepared using CVD method, right? Chemical vapor deposition. This is a chemical reaction. Silane reacts with oxygen, leading to silicon dioxide thin film. The deposition temperature is typically 450 Celsius. And we call this type of oxide low temperature oxide, LTO. Note that this chemical reaction, namely silane reacts with oxygen, can also be carried out inside a plasma. So plasma enhanced CVD. Then the deposition temperature can be significantly reduced. So now we can deposit silicon dioxide at 200 degrees C, at 200 Celsius. And that's a PECVD. Silicon dioxide can also be deposited using different gases, like for example, TEOS, that's a different gas, or dichlorosilane plus N2O, nitric oxide. The deposition temperatures are 700 and 900 Celsius respectively. So compared to these two CVD processes, right, this silane plus oxygen reaction has a lower temperature. Okay, that's the reason we call this low temperature oxide. Right? Even though its deposition temperature is 450 Celsius, it's pretty high. Okay, but it's lower than the other two processes. And previously, we also learned that silicon dioxide can be grown on silicon substrate using thermal oxidation. Okay, thermal oxidation. So that's a thermal oxide. So now let's have a comparison of silicon dioxide prepared by different methods. Right? PECVD, LTO, right? TEOS, right? dichlorosilane, and thermal oxide. First deposition temperature. Right? PECVD has the lowest deposition temperature, 200 Celsius, 450, 700, 900, 1000 Celsius. Step coverage, PECVD, non-conformal. LTO, non-conformal. Conformal, conformal, conformal. Right, so the higher the temperature, the better the step coverage. Right, that's because we discussed the step coverage in the last lecture. Right, step coverage is determined by two factors: surface mobility and mean free path. At a high temperature, the surface mobility can be very large. Okay, so if we have a high surface mobility, we can always get uniform coating, a very good step coverage. Okay. So that's the reason the three high temperature processes have good step coverage. Refractive index about same. Stress, the building stress. The plasma one can be either compressive or tensile. LTO is tensile, right? TEOS, compressive. Dichlorosilane plus nitric oxide, compressive. Thermal oxide, compressive. Dielectric strength. Dielectric strength refers to the capability of the thin film to withstand voltage before breakdown. Okay, so we can see the unit is a milliamp volt per centimeter. For plasma one, 3 to 6. Aotl 8, right? 10, 10, 11. Next, etch rate, right? Nanometer per minute in diluted HF. Plasma 1, 40 nanometer per minute. Aotl 6, 3, 3, 2.5. But know that in some sense, the dielectric strength and the etch rate in HF can indicate the quality of the thin film. So we can see that the higher the temperature, the better the thin film quality. Okay, so there's always a trade-off. Okay, we want to lower the temperature for the convenience of the deposition, but the quality of the resulting thin film is not as good as high temperature ones. Okay, PSG. Well, we previously used the PSG to dope polysilicon. PSG stands for phosphosilicate glass. It's prepared by using these two chemical reactions. The first one is same as the one for Aotl, right? Silane reacts with oxygen, right, which gives us silicon dioxide. The second one, phosphine, reacts with oxygen, leading to P2O5. This is it's called phosphorus pentoxide. Okay, we have 5 here, so it's pentoxide. So PSG is simply a mixture of silicon dioxide and phosphorus pentoxide. Or you can consider it as a silicon dioxide doped with phosphorus. Okay, it is a source of phosphorus. Advantages of PSG over Aotl. Right, sometimes we prefer PSG over Aotl for the following 2 reasons. First, PSG has a faster etching rate in HF, right, as shown in this table. Right, PSG has a faster etching rate compared to that of Aotl. Second, PSG can reflow during high temperature annealing. What does this mean? To answer this question, let's take a look at these figures. These figures actually plot the reflow of PSG after 20 minutes annealing at 1100 Celsius. Figure A shows a case with 0% phosphorus. So in case A, what's shown in this figure is Aotl, right, silicon dioxide, not PSG. Right, there's no P2O5 in the thin film. So actually, it does not reflow. Right, so this figure actually shows a thin film profile as deposited. Okay, and this is actually consistent with our previous discussion. Right, the thickness of thin film is proportional to the arriving angle. Okay, so this convex corner has the thickest film, right, and this concave corner has the thinnest film. So that's what we expected. So no reflow with a 0% P. Figure B shows a 2.2% phosphorus. Figure C, 4.6%. The figure D, 7.2%. And we can observe that as the phosphorus concentration increases, the reflow becomes more significant. And this helps to planarize the surface. So it is desirable for many applications. So we prefer, so in many applications, we prefer PSG over Aotl. Right? For Aotl, no reflow. Polymers in films. I know that polymers are also popular materials for surface machining. And the polymers in films can be typically prepared using spin coating. Some examples include polyemite, Teflon, silicone, rubber. This slide summarizes the properties of polyemite. And we can see that polyemite has a good mechanical and thermal property. Its Young's modulus is between 1 to 10 gigapascal, elongation and break 10 to 100%. Decomposition temperature is greater than 400 degrees C, right? 400 Celsius. Okay, so it has a fairly good thermal stability. Applications of polyemite in MEMS. Flexible temperature sensor array, floating element shear stress sensor, flexible ribbon cable, silicon force sensor, flow sensor with a polyemite as a thermal insulation layer, flexible shear stress sensor skin. We can see that my polyemite is mainly used as a flexible mechanical material. Other materials which can be used in certain micromachining and also broader MEMS devices. Piezoelectric materials such as quartz, zinc oxide, PZT, aluminum nitride. But later we'll have very detailed discussion of piezoelectricity. Silicon carbide, which is prepared using CVD method at very high temperature. Diamond films, which are also prepared using CVD method. And the metals, all kinds of metals, such as aluminum, nickel, this is a nickel iron alloy. We typically call this terminal if the ratio is 80 to 20. Copper, gold, platinum, so all kinds of metals.